7.2, yes. All right, welcome back, everyone. So last class, we finished up 7.1, which was the law of sines. It was a pretty lengthy section because of all the different cases. We had the nice easy case we did at first where we were given two angles. Then we had the ambiguous case where we had to determine whether it was no triangle, one triangle, or two triangles. A lot of little weird oddities in that and just things to keep track of. And now we're finally ready to do the final case of being able to solve a triangle as long as we have 3 bits of information. So as a reminder, the law of sines was when we had a triangle and you knew like this side, and this angle, something like that, where this angle was not between them. This was a law of sines scenario, and this was the ambiguous case in particular. Law of cosines is going to be where maybe we had the sides A and B still. Also, I wrote that as a C, and that is completely wrong. That is not angle C, that is angle A. Please forgive me for that. Law of sines, you'd be given this bits of information, or angle B, either angle A or angle B, but you could not be given angle C. The law of cosines is when we do know angle C, or angle gamma, whichever you prefer it. So this is where we have that, what I call a corner of information. That's when we use the law of cosines. Now, when we have a corner of information, we're going to have some things that could mess us up along the way. We're going to have to be very careful. You can punch things in a calculator and it'll give you answers, but if you weren't careful at one point throughout the problem, all those answers can actually be wrong. It has everything to do with how inverse sine and inverse cosine work and how they are bound. I've mentioned several times throughout this class that issue will keep kind of coming up here and there. So those are the 2 scenarios we're looking at. Law of cosines, explicitly this, a corner of information. Now, that is one of the scenarios, or you can also have the scenario where you know all 3 sides. You know this side, and this side. And you might be thinking, well, Mr. Beckner, you told me that the 3-angle situation isn't even solvable because it's infinitely many side lengths. And that was true, but that's not this scenario. If you know these side lengths, then these angles are a fixed value. There's not going to be infinitely many possible angles to solve that. So this is the side angle side, the SAS case. Don't give your teacher any sass, ha ha ha. And this would be the side case, whereas the law of sines was side angle. And we said, we don't do it the backwards way for obvious reasons. So again, law of cosines. So law of cosines is needed for the sine angle side case, again, the corner of info that I like to call it, and the side case. You can't start out those cases with law of sines. You will need the law of sines ultimately, but you can't start the problem with the law of sines. So I'm going to give you 3 formulas. Admittedly, all 3 of these formulas are the same, just with different letters, kind of like the area of an oblique triangle. I said there was 3 area formulas, even though they were all the same, just with different letters. Kind of like the law of sines had 3 sides, which are all the same, just with different letters. So our formulas. No proof, just giving them to you. This would be completely awful to prove. One of the worst things to prove for us. A squared equals B squared plus C squared. Oh, that's just Pythagorean. What are you talking about? No, that ain't it though. Minus 2BC times the cosine of angle A. So if you had the side lengths B and C and angle A, you could find the length of A based on this formula. Now it says A squared, so you'd have to square root it. If you think you need to plus or minus square root it, that's a great idea, but geometry, we generally don't need the minus because you can't have negative lengths. All right, the next formula is B squared equals, and then it's literally going to copy paste this, except instead of B's and C's, there'll be A's and C's. Instead of this being B and C, it'll be A and C, and instead of this being angle A, it'll be angle B. So we go a squared plus c squared minus 2ac times the cosine of angle B. Or the third version, c squared equals, I think you know or have an idea of what these might be. So that's c, so these are the a's and b's, and then minus same product, 2ab, and then a cosine of angle C, capital C. You must memorize at least one of these formulas or all three if you really feel the need. Me personally, I really like this one if I was just going to memorize one and then cookie cutter the rest to fit it. Some people really like this one because then you've got the C solved in terms of A's and B's. It's up to you. Some people say I memorized all three just on themselves. Whatever works for you, but that doesn't seem like a great idea to me. Because these are so similar, just remember it conceptually. One leg squared is the sum of the other leg squareds. If you just had this just looks like Pythagorean. Although it would have been c squared equals a squared plus b squared, but remember this isn't a right triangle, so don't try and relate it too much. So what you might even say is, okay, well you said Pythagorean and this one has c squared, so maybe that's why you like this version. So you have the Pythagorean part, but then there's an extra little detail. This basically just accounts for the fact that it's not a right triangle. This factor being subtracted is just a, how do I want to phrase it? It fixes it. It accounts for it. So this right here kind of looks like a factoring formula, minus 2ab, 2 times the product. It would have been like a squared minus 2ab plus b squared, the pre-factored version that is, but then the cosine of the angle between them. This letter should match this letter. This letter matches this letter in terms of lower and upper cases, that is. So I don't care which one you memorize to get all three, or if you're memorizing all three, or whatever it is you're doing, but I will not give you that formula ever on a test. Final, anything. You got to know them. So again, that's for a corner of information, something that looks like an angle C and then side lengths A and B. So SAS, I'll finally write it down, is a corner of info. It's not literally a corner. I mean, I'm not saying it's just this is the corner. I'm saying imagine that you didn't draw, oops. Imagine that you didn't draw the other side of the triangle. That's your corner. But of course, the triangle is completed. All right, so before we try this out, I need to point out something extremely critical. So lots of asterisks for this one. Remember, the law of sines, excuse me, that the inverse sign is only valid from negative 90 degrees to positive 90 degrees. In other words, quadrants 1 and 4. This means that if you try to find an angle larger than 90 degrees, you can't by using inverse sine. You can't do it. Your calculator is going to tell you an answer that is wrong. It's not going to say it can't do it. It's just going to give you a wrong answer. Because it's going to get this information and think, oh, okay, well, if you've got these lengths of sides and these other angles and such, and you know, that would mean it's going to be positive or negative, whatever. I'm just going to give you an answer of quadrant 1 or 4. If it's positive, I'll give you an answer in quadrant 1. If it's negative, I'll give you an answer in quadrant 4. But if your angle that you're supposed to be finding ends up being, say, 115 degrees, which would have been quadrant 2, inverse sine isn't valid there, so it's going to say, all right, well, it was positive, so I'm just going to give you the reference angle put in quadrant 1. Now, with that trick, you can, if you know all of this stuff is happening, you can then put that reference angle in quadrant 2 to find the real angle. But I'm gonna say that probably 99% of people don't ever consider that, admitting that even I have made that mistake. So I've already mentioned that with these law of cosines problems, when you're given a corner of information, you'll start out with the law of cosines, but then to find the other information, you're going to go back to law of sines because you'll now be able to, and it's a much easier formula to use. So this means if you try and find an angle larger than 90, you can't. But how are you going to know? Because you only have one angle initially. The second angle you'll find by law of sines. The third one you'll find by doing 180 minus it. So how can you tell whether an angle is going to be greater than 90 or not? You can't, but you can at least throw out the scenario that it might be greater than 90. So here is your hint, your approach, not necessarily a hint. So to avoid this possibility, when you do law of sines, find your second angle, make sure that you are not using the largest, let me say longest, side. In other words, do not find the angle opposite the largest side. So this is why that's going to work. The largest angle must be opposite the largest side. So if there is an angle bigger than 90 degrees in the triangle, there could only be one of them. So let's say that 115 degrees. There's no way you can have another angle that's bigger than 90 degrees because even if it was 91, 91 plus 115 is more than 180. So there's only one angle that can be bigger than 90 degrees, and that angle will always be opposite the largest side. So just don't use the largest side in the law of sines, and boom, you'll make sure that you don't have that issue when you put it in your calculator. I will again point this out. I have made this mistake. I've made this mistake in class teaching it before. I am literally looking at notes. I keep this from many years ago. I have one problem that I always keep to remind myself. I taught one wrong initially, and then I looked at it and it was like, uh-oh, we used the law of sines on the longest side. Didn't mean to do that. So I keep that as a relic, and I'm going to keep it for the next 20 years for the same reason. It's a nice thing about making mistakes. When you make mistakes, you'll learn not to make them again as long as you figure out that it was a mistake. All right. Now, this issue with inverse sine, this issue might also happen with inverse cosine later, maybe, maybe not, or maybe we're going to use inverse cosine on a specific parameter to make sure that this can't happen with the law of sines, but it's going to come up again. That's all I'm going to say, but not yet, not for a while. All right, so with all these details said, we got our formulas that we'll scroll back up to, at least for the first problem, maybe the second problem. We know that when we get to the point where we're doing law of sines, that we're not going to attack the largest side because that would find the largest angle, and that might be bigger than 90, and inverse sine wouldn't pick it up. Okay. So here's your process. Here's the order you should do things. In the SAS case, do a law of cosines first, find the third side. I know what's going on. I want to, whoop, not that button. Do this, remove. Boom, there we go. Do law of cosines to find the third side first. That was going to bug me. Then do the law of sines, not with the largest side's angle, to find second angle, and then do 180 degrees minus the two angles to find the third angle. So I'm going to go ahead and spoil something. There is no second triangle possible with these. It never is, never will be. There's always one triangle. It's never none, it's never two, it's always one. So this is our process for the side angle side. Do a law of cosines, then a law of sines. Make sure you're not finding the angle opposite the largest side. Now, if you already have the largest side and the largest angle, that's okay. If you already have an angle prescribed to you that's bigger than 90, the issue won't even be an issue. All right, so let's get it. Let's try one. Example 1. Complete the triangle. I can give you these as an image, or I can give them to you as a list of just parameters. Let's go back to giving you an image. this will be A. So let's go triangle. Don't assume this is equilateral or right or anything like that. I'm going to call this side C. I'm going to call this angle 32 degrees. This side length will be 10, and this side length will be 12. I didn't have to call that side length C. I could have called it A. I could have called it B. I'm just choosing to call it C. I'm calling it C because that's how I'm going to use my formula. I'm going to go with the third version of the formula, which you can still see peeking at the top of the screen right here, because I find that a lot of people prefer that one. I may have actually said earlier, incidentally, or accidentally, that I like the first one. That's wrong. I do like the third one. I like this one because it looks like Pythagorean, then it kind of looks like a factoring formula. I like being able to relate things to other things I already know. It's less memorization. Patterns are wonderful. All right, so I get to call that C because I never was given any assumptions on letters. So that was my choice, which would make the rest of everything, I could call them angle A and B, or angle A and B in whatever order. I'll decide that later. So for now, C squared equals, I'll write the formula I'm going to use. A squared plus B squared minus 2AB cosine of angle C. So this would be C squared equals, I'm going to call the A the 12, so this will be 12 squared plus, then that makes the B the 10, 10 squared minus 2 times 12 times 10 times the cosine of 32 degrees. Now, if C squared is equal to that, we could go ahead and put this in a calculator, and it's going to give me a whole bunch of decimals. That's whatever. But I like to go ahead and show that C would then be the square root of everything. If C squared is this value, that means C is the square root of it, not plus or minus, because we're talking about a length of a side, there is no minus. So the square root of 12 squared plus 10 squared minus 2 times 12 times 10 times the cosine of 32 degrees. I'm going to put this in a calculator. That's why I'm not even writing that that's 144 and that's 100 and 24, 240 cosine of 32 degrees. I'm just going to jam that in the calculator as you see. That was my pre-calc class earlier. Ignore that. So big old square root, 12 squared plus 10 squared minus 2 times 12 times 10 times the cosine of 32 degrees. We should probably make sure we are in a are in degrees. We are, that's good. Drum roll, ba-da-da-da-da-da-da. We get 6.36, and I'm going to do my usual round to the nearest tenth. So this is approximately 6.4. Let me pull that calculator up for another second so you can keep seeing that. See, if I'd done all the 12 squared stuff first, let me just pull that up, delete the square roots. If I do this as two steps, so do all the math inside the square root, square root of 40.46, and then take the square root of the answer, you still get that. But notice if I take the square root, let's say I rounded that to 40.5 before I took the square root, which is a bad idea. Now this answer is still pretty close. It's still going to round to 6.4, but you can see that it is not exactly the same, so that truncation or round off error, taking let me start that over, taking a number that's been rounded and processing it and then rounding it again, you can see how that could have ended up staying at 6.3 after rounding, or maybe it bumps way up and it becomes 6.5. That's why I just don't like to take a rounded number and process it. That's why I did square root of answer, or type literally square root of 40.46, blah, 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 blah. It's not the end of the world. I will say 9 out of 10 times, maybe even more than 9 out of 10 times, that rounding that to a tenth before square root is going to be okay. But you're going to be mad when that 1 out of 10 times happens, aren't you? So just best to leave it alone. All right, so now we'll use the law of sines to find, so let me go back and label things. We said I called that C, so that was opposite angle C. We called the 12 little a, so that means this is angle capital A, and that would be angle capital B. So some people will think we can use the law of sines to find either of angle A or B, but that's not quite true. Sometimes it's true, sometimes it's not. And if you don't know which case you're in, you're going to get it wrong maybe, I don't want to say half the time, but you'll get it wrong sometimes. All right, so use the law of sines to find. All right, make sure you are not using the longest side. So the longest side up here was the 12, so do not find A. We don't want to find A with the law of sines because it's possible that that angle is bigger than 90. It's possible, it's not a guarantee. We don't know right now, we don't want to risk it. So we've got to find angle B, we have to. Otherwise we're flipping a coin and putting fate in our hands. So law of sines, that's A over sine A equals B over sine B equals C over sine C. The thing we have completed are the C's. Now you might say, well, Mr. Beckner, you said you don't like using rounded numbers. We don't really have an option at this point. If you wanted to, in that formula, put the big, beefy 6.36, blah, 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 you can, but let's just roll with the 6.4. So 6.4 over the sine, not cosine, of 32 degrees equals, now we got to go after the B's, which was the 10 over the sine of B. We're going to cross multiply, which will give us 6.4 sine of B equals 10 times the sine of 32 degrees. We're going to divide both sides by 6.4, which will give us that the sine of B is equal to 10 sine of 32 degrees over 6.4. And then we take the inverse sine of both sides. Like so. We do that because inverse sines and sines cancel, but only if we're in quadrant 1 or 4, which, as we said, A could be bigger than 90. So A could be in quadrant 2, so we wouldn't be able to guarantee that this aspect is true if we attacked A. But for B, because it's not opposite the largest side, angle B is definitely less than 90. So B will be the inverse sine of all that jazz, which when we round to the nearest tenth, let me do this. So, that's a little too much, isn't it? Here we go. So, inverse sine 10. What happened? 10. Then the sine of 32 and close it, divided by 6.4 and close it. And we end up with 55.89, blah, 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 blah. So rounded to the nearest tenth, that's going to be 55.9 degrees. So B is approximately 55.9 degrees. Now your homework might say round to the nearest whole, and admittedly, because we rounded because we rounded this to the nearest tenth, I have a strong feeling that this is probably off by a couple of tenths, maybe 2 or 3 even. It's probably like 56.1, 56.2 maybe. If I had used the exact number in there instead of 6.4, so that was, let me show you what I mean. If I bring this whole problem back, instead of doing 6.4, let's go 6.36148229, then close it. And I was right. We're off by about 1/2 of a degree, in fact. That is the error propagation I keep talking about. So again, this is going to be good enough for us. I believe that my math lab for these types of problems tends to tell you to round in the nearest whole because of that, because both of these would have rounded to 56 degrees. But let's just go with what I have on the screen. Let's accept the very small error just for the sake of completion. All right, so that was angle B. So we've got length C. We've got angle B, which means the only thing we have left to find is angle A, which we just do the 180 minus the rest. So A would be 180 minus the 32 degrees minus the what I'm calling 55.9. I've already showed you that this is not exact. And if you really want to pull out the calculator if your brain's hurting at this point. Feel free. It's already staring me in the face, so I'm going to use it. And you get 92.1 degrees. That's a weird looking 9. So if we had used the actual answer, or a much better answer of 56.4, we would have done 180 minus 32 minus 56.4. So 91.6 is a much more exact answer, but I'm saying that 92.1 is perfectly fine for what we're doing here. And look at that. This is bigger than 90, which means if we had done the law of sines to find angle A, law of sines on A would fail. Don't believe me? Check it out. So in blue, I'll just show you that fact. So let me pull back so I can see everything. So if we tried to do the A's, we would have gone for the C's, that was the 6.4 over the sine of 32 degrees equals 12 over sine of A. After you cross multiply and solve, I'm not going to show all the work, you'll end up getting that the sine of A is equal to 12 sine of 32 degrees over the 6.4. So A would be the inverse sine of 12 sine of 32 degrees over 6.4. So let's type that out and see what happens. Inverse sine 12 sine of 32, close, divided by 6.4. And we get 83.5 degrees, which is not the answer. It is wrong. It is wrong because the thing that is inside of it is a positive value. So the inverse sine function in your calculator is going to assume that we're supposed to be in quadrant 1, but in reality, the construct of this triangle, this is 91.6. I think that was yeah, 91.6, which we called 92.1. We accepted the half off. It's fine. But again, because your calculator thinks this is supposed to be in quadrant 1, it gives you an answer that's in quadrant 1. And it's wrong. And it's not like you can just take the reference angle of this, and put it in the other one. It would not give you the correct answer. I might have said that earlier. I said it might work, but in fact, it actually doesn't. Taking that as a reference angle and putting it in quadrant 2 would actually give you like 97 degrees roughly, 96.5, something like that. So that is why you have to be very, very careful. And again, if that angle wasn't bigger than 90, it would have been fine, but you don't know whether it's bigger than 90 or not. The only way you would know is if the angle we gave you, if this was bigger than 90. And guess what? I don't like giving you angles that are bigger than 90 because I want you to be on your toes. I want you to know these ins and outs of this weird scenario. Because these little issues can become major ones in the long term. Imagine you're working for a construction company and you actually have to do some of this math, which is absolutely possible. And then you build your frame incorrectly or whatever it is you're doing with this triangle. I know triangle frame, it's not exactly normal, but you get the point. I'm saying you could build something wrong, you take it to boss man, it's like, why'd you make this an 83-degree angle? It's supposed to be 92. Come on, get with it. And if it's the 5th time you've done it, maybe he fires you. So don't get fired. Nobody wants to get fired here. Gotta make that bread. But the process itself is normalized. Law of cosines, then law of sines, then 180 minus the rest. Just when you do that law of sines, you got to be careful. All right, so let's do another one. And I'll give you the image for this one as well. So let's give you a triangle that looks like this. Again, if it looks equilateral, don't assume that. If I say that's 10 degrees, it's very obviously not an equilateral triangle. It'd have to be 60 for that to be the case. This is not drawn to scale. No mathematician draws us triangles to scale. And then this is a 31. So I've given you a corner of information, side, angle, side. We don't go side, side, angle because it's a lot easier to go this way. Someone might think, oh, side, side, angle, but we would want this side to be the next thing we have, not this one. We're skipping too much to call this side, side, angle. All right, so that's law of cosines. No matter what you decide to call these things, it doesn't matter. I want to use a different version of the formula. So I'm going to use the one that says a squared equals b squared plus c squared minus 2bc cosine of angle A. So that means I'm calling the 24 and the 31 the b and the c, which means the 10 degrees has to be my angle A. So I am deciding to call this A. The 24 and the 31 I could call B or C in any order. I'm going to choose to call the 24 the B for no particular reason, and the 31 the little c. Again, my choice here was arbitrary. I didn't have to do these. I could have called the 24 little a, the 31 little b, and this capital C for the angle. The cool thing is when you plug those numbers into the formula, no matter which of the three formulas you use, no matter which of the three lettering choices you use, all the numbers will look exactly the same. All right, so our little a, so we'll have for our law of cosines, we get a squared equals 24 squared plus 31 squared minus 2 times the product of those, 24 and 31, and then times the cosine of our angle, which is 10 degrees. And you are more than welcome to square the 24 and the 31 and multiply all that other jazz out. But it's honestly not worth the effort because if this is a squared, you know you're just going to take the square root and you know that you're going to jam all those numbers in a calculator. So why bother simplifying along the way? If you simplify along the way, you're bound to make a mistake somewhere. So that's exactly what I would type into my calculator right there. Just keep it simple. All right, so let's do it. Big square root, 24 squared plus 31 squared, then minus 2 times 24 times 31 times the cosine. I don't actually have to hit times, but I like doing it anyways for the 10 degrees. And then we close up the parentheses for the cosine, close it for the square root. Admittedly, since it's at the end with this calculator, I don't have to, but again, it's just good notation. And we end up getting 8.46 blah, 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 blah. We're going to round to the nearest tenth. So that's about 8.5. Now, again, what you might want to try out on your own, just kind of studying this concept of error propagation, maybe do all of the math besides the square root, the 24 squared plus the 31 squared, blah, 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 hit enter, and then round that to the nearest tenth, then take the square root of it. I'm pretty sure that you're still going to get that 8.46, but then after that, it's going to be different numbers, and you'd still round correctly. And what's cool in calculus and beyond is you actually study the error propagation of functions themselves without putting any numbers in there. And you can talk about how square roots errors actually don't propagate too poorly. Whereas if you have like an x squared or an x cubed, they do propagate, and the bigger the exponent, the worse it propagates. And that's because cubes make numbers bigger, so it would make an error bigger. Square roots makes numbers smaller, so it would probably make an error smaller. That's a very basic concept of it. But actually doing the calculus of it, it gets pretty hairy. But it's some good math. And it's very, very important in the grand scheme of our world. All right, so my error propagation rant aside, and the funny thing is I'm not even a huge fan of doing that math, but I love the concept of error propagation. We got our little a being 8.5. So we know this is 8.5. We could put it there if we wanted, but I don't want to. So we know that's the 8.5. We now have 3 sides and an angle. With 3 sides and 1 angle, we can now find another angle. We can either find maybe the angle opposite of C or B, but we said we need to be really careful. We need to make sure that we're not using the largest side because that angle could be bigger than 90 degrees. It's not a guarantee. So that means we can't use the 31 yet in our law of sines. So for law of sines, we have to use what I've called B. We have to use the 24 with the completed A's. So the A over the sine of A would be 8.5 over sine of 10 degrees. I have to use the 24 over the sine of angle B. And I'm going to go to, no, I already did a capital, so I'll stick with capital. Again, you absolutely should not be using the 31 over sine of C because that angle could be incorrect if it happens to be bigger than 90, which we don't know yet. You're going to cross multiply. You'll get 8.5 sine of b equals 24 sine of 10 degrees. You're going to divide both sides by the 8.5. You get used to the pattern of the math, I hope. And you get sine of angle B equals 24 sine of 10 degrees over the 8.5. You're going to take your inverse sine of both sides. And I'm going to skip showing that work this time. The inverse sine and the sine will cancel because we know B is under 90 degrees because it wasn't opposite the largest side. So B is equal to the inverse sine of all that jazz on the right, 24 sine of 10 degrees over 8.5, which when we round to the nearest tenth after jamming in a calculator, let me clear the screen, it's getting a little jumbled. Inverse sine, 24 times the sine of 10 degrees. Now this one you absolutely have to close. Divided by 8.5. It's the trailing ones that I don't technically have to hit this one, but I like to. And we get 29.36 blah, blah, blah. So rounded to the nearest tenth is 29.4 degrees. So that's what we're going to call angle B. We already had side A. So knowing two angles, the 10 degrees and the 29.4 degrees, we can find our third angle, which we're calling angle C, capital C. So 180 minus the others. Which ends up being, so that's 170, 140, then kick back the extra 6, so 140.6. That's our third angle, which is bigger than 90, which means the law of sines would have failed. I'm not going to show that failure this time. Feel free to show it on your own, like I did at the end of A. If you did this law of sines with a 31 here, and the angle C here, it would end up being wrong when you solve for that angle C. I 100% guarantee that. You will get something like 70 or 60 or 50 degrees, somewhere in that ballpark probably. I'm guessing, which is completely way off from what the answer actually is. Last time they were pretty close to each other, and that's because we were just barely in quadrant 2. Now, because we're really trucking in quadrant 2, that means that the calculator would spit out a very, very wrong answer. All right, so we got our 3 components. And remember, you can always put your answer all together in one box. In my math lab, it's going to have the specific spots for everything. So 8.5 is A, then 29, why am I writing the numbers first? B is 29.4 degrees, and C is 140.6 degrees. Again, on scratch work, I don't care if you're just boxing off as you go, or if you put it all together. Either or is fine. I care that your work looks good, you've done everything in the right order, all that stuff. All right, let's do another one. Can I fit it all here? Yes, we can. C. And this time I'm going to label them instead of giving you the triangle. A is 19. C is going to be 4, and then angle beta, let's go back to Greek, will be 61 degrees. Now, it's not as obvious that this is a corner of information. Maybe you need to draw it up, but remember, a corner of information means you have the angle between, and the angle between means you don't have one of these angles. So this is a corner of information. If you drew it up, it would be like 61 degrees is here, this is your 19, and this is your 4. Obviously not to scale. And then your other end is over there. And that's your corner of information, which means we need the law of cosines. You can't start with the law of sines. You absolutely, positively must start with law of cosines. It's the only way to get anything else right now. Now, I've labeled these as A, C, and B, which means the formula we're going to need to use is going to have side B by itself. Sorry, I was looking at something else, and I was like, that's not right. But we'd use the one with B by itself, the little b. So A squared plus C squared minus not equals, got a little squirrely with my pen there, minus 2AC, then a cosine of angle beta. So we get b squared. And some people will just say, can't I just go ahead and write b equals the square root of all of that? Yes, you can. I'm just being methodical. So 19 squared plus 4 squared minus 2 times 19 times 4 times the cosine of 61 degrees. Take the square root and you'll get b equals the square root of all of that. 19 squared plus 4 squared minus 2 times 19. Doesn't look like I have the 1 in there, does it? Times 4. I'm just going to make that a little better. 2 times 19 times 4 cosine of 61 degrees. And then round to the nearest tenth or whole or whatever my math lab tells you to do. Please pay attention to the instructions. Wow, I missed that thing, cut off on me a quarter of a second, if not less, before I hit a button. Square root 19 squared plus 4 squared minus 2 times 19 times 4 times the cosine of 61 degrees. And we get 17.4 when we round to the nearest tenth. So that's what we're going to call our length B. Now we do, so that was the law of cosines. Now we do the law of sines. Now, we cannot find the angle opposite the largest side. The largest side is 19, so I cannot find angle A doing this. It could be wrong. And now the first two I designed so they would have been wrong. Maybe this one I will too, maybe not, I don't know. Hint, wink, nudge. But I do love problems that are forcing you to do it the correct way. That way it keeps you on your toes. All right, so I can't use the A's, I gotta go after angle C. So what do we have completed? We have the B's completed. So we're gonna go 17.4 over the sine of 61 degrees, that's the B over sine of B, equals C over sine C, so 4 over sine of capital C, or gamma in this case, since I'm going Greek. Now, once again, rounding this to the nearest tenth, putting it in here, that causes error propagation. This angle will be off by a few tenths of a degree, but no more than a few tenths of a degree. If you don't want to be off, then use the more exact answer here, 17.415766693. But like I said, I think the homework tells you to round in the nearest whole for these because of that, because then it's not really an issue. Cross multiply, you know what it is, 17.4, at least I hope you do at this point, sine of alpha equals 4 times the sine of 61 degrees. Divide both sides by 17.4, giving us the sine of gamma equals 4 sine 61 degrees over 17.4. Take the inverse sine of both sides, ultimately giving us that gamma is equal to the inverse sine of 4 sine of 61 degrees over 17.4. And we know that gamma will be less than 90 because C is not the largest side. Round to the nearest tenth, or whole, or whatever the problem tells you to do. Inverse sine. 4 sine 61 degrees. Close it. Divided by 17.4, or the more exact, if you want a more exact answer, close it. We get 11.59 blah, 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 which will be 11.6. This is an angle, so degrees. That's 61, that's 11.6. I'm willing to bet $1 million that other angle is bigger than 90. How do we find the third angle, which we're going to call alpha? It's 180 minus the others. 180 minus the 61 minus the 11.6. So what's that? 119, 108, so 107.4. That's our alpha. And since that's bigger than 90, we would have had issues with the law of sines. How are we on time? 30 minutes? Oh yeah, we're gonna finish this section today. And then we'll call it after that. So that was 3 examples of the side angle side case. 2 sides in an angle. But 2 sides in an angle doesn't tell you whether you're starting off with law of sines or cosines. You've got to know whether they're all tucked in a corner, or if the 2 sides you know are kind of next to each other and then the angle is not the angle between them. Distinct differences there. If I gave you 2 angles, easy case. If I give you one angle, it's either the ambiguous case with law of sines, or it's the law of cosines if it's the angle between them instead. But we have not studied the final case, which is when I give you all three sides and no angles between them. And you might go, well, hold on, these are all solved for sides. How do you find an angle? Well, there's an angle in each one of these, so you would just take those equations, those formulas, and you solve them for the angle. Now, nobody wants to just blatantly memorize those where it's inverse cosine of a squared minus b squared minus c squared over negative 2bc, and then two more variations of that. That sounds awful. Just just plug the numbers into the original formula and do your algebra and solve it that way. And it's algebra that you better know how to solve, better know how to handle that SSA. So for the side case, last possible case for giving you a triangle with three components and you can fill in the rest, and they aren't even a right triangle anymore. So at this point, we've pretty much done all the essential trigonometry we need without going into a more advanced version of trigonometry where we start doing something called vectors, and that'll be the next stuff we do in here. And it's not like it's crazier, it's just, you're thinking about graphs a little differently. Instead of just having points, we're gonna have arrows, but let's save that for next time. So it's the side case. We're gonna have that, if you end up doing a inverse sine of an angle bigger than 90, your calculator is gonna give you a wrong answer. That's still a possibility here. So to avoid that possibility, what we wanna do is always find the angle opposite the largest side first. This will avoid doing an inverse sine of an angle that could be bigger than 90. That's what that'll do for us. So we'll go ahead and knock the largest angle out first. Then we know the other two are going to be less than 90, and we no longer have to keep our ducks in a row. Admittedly, it's not the only way to make sure that doesn't happen. You can attack whatever angle you want, and then in the second step, when you do law of sines, just make sure that you don't attack the largest one. But I just think it's better to do this. Just go ahead and find the largest angle, which is going to be the angle opposite the largest side. Now, with the side case, you're doing law of cosines. You should always find the angle opposite the largest side first. Let me be more specific, by law of cosines. The law of cosines is valid in quadrant 1 and 2. The law of cosines can pick up angles between 90 and 180 degrees. If you go back to the definitions of their bounds, which we've discussed many times, inverse sine is quadrant 1 and 4, inverse cosine quadrant 1 and 2. And I know that seems like such a subtle detail to have to remember, but you have to remember it. So inverse cosine can pick up an angle between 90 and 180, so let's go ahead and get that out of the way. That way, when you go for the second and third, you're not juggling anything anymore. You can do whatever you want. So after you've done that, then use the law of sines to find the second angle, then 180 minus the others to find the third. It's literally the same process. Law of cosines, then law of sines, then supplement. I should say supplement in quotes, because it's two angles, not just one, being subtracted. Some people might say, well, could you use law of cosines to find the second angle? Could you use law of cosines to find the third angle? Yes, actually you could. It is extremely inefficient though, because the law of cosines formula is that big beefy thing, whereas law of sines is much shorter, and using 180 minus the others is ridiculously short. So this, what you see on the screen and what I've said is the most efficient method. It's not the only method, but that's the way I'm going to do things. All right, so example 2, the triangle. And for A, we will give you the picture. And I'm going to go 9, 12, and 11 clockwise. Please pretend that that was connected appropriately. Now, I did not say whether these were A, B's, or C's initially. So you get to decide which is A, which is B, which is C. I'm going to now make the decision that I'm going to call the bottom left one angle A. I'm going to call the bottom right one angle B, and the top one angle C. That was my choice. That's a capital C up there. I know it doesn't look too capitalized, but it is. What some people like to do for their capitals is something like that. Give it a little extra dash. And that's perfectly fine. Something I used to do, but I don't anymore. And that's because in my own notes, I don't actually use capital letters. I always use Greek. All right, so I gave you three sides. Law of sines requires at least one angle known, so we can't do that. 180 minus the other two requires knowing two of the other, so we can't do that. But the law of cosines formula has a single angle in each of the formulas based on two or three other sides. So we could just algebraically solve for this after plugging in some numbers. It's going to be a decent amount of algebra, but it's algebra we know how to do. So I said we should always attack the largest angle, which is opposite the largest side. I have called the 12 the little a, that's the biggest side, which means capital A would be the biggest angle, so that's the one we need to find first. So the formula I need to use is the a squared equals b squared plus c squared minus 2bc cosine of capital A. With this lettering, this is the one I have to do first to make sure I don't mess something up later, to make sure that we go ahead and find the biggest angle now so we don't screw up later. Plug in the numbers and we get a squared, that's the 12, equals b squared, which is the 9, plus the c squared, which is the 11, minus 2 times 9 times 11 times the cosine of angle A, which we don't know. And we got to solve for angle A. All right. Well, this time we are actually going to have to process these numbers because we got some algebra to do. So 12 squared is 144, 9 squared is 81, 11 squared is 121, minus 2 times, let's make this easier. 9 times 11 is going to be 99, and then 2 times 99 is 198. And the cosine of angle A. All right, if we combine what we cannot subtract the 198 that's attached to a cosine. So it's just the 81 and the 121, which will make 202. So that's 144 equals 202 minus 198 cosine of angle A. Then we just got to keep doing our algebra. So we're going to subtract 202 on both sides, which will give us 144 minus 202, what's that, negative 58. And then that's negative 198 cosine of angle A. We're going to divide both sides by the negative 198. It's a lot more algebraically intense than before, I know, but the negatives will cancel. Let me just go over here for space conservation. I'm not going to worry about reducing that fraction because we know it's going in a calculator. 58 over 198 equals cosine of angle A. And then we take the inverse cosine of both sides to cancel out that cosine. So we get inverse cosine of the 58 over 198, and then inverse cosine of the cosine of A. The inverse cosine and the cosine will cancel as long as we're in quadrant 1 or 2, which we definitely are. All triangles have angles between 0 and 180, so it would be impossible otherwise. So that says the inverse cosine of 58 over 198 should be angle A, which will round to the nearest tenth. Inverse cosine, 58 divided by 198. Drum roll. 72.96, which the 0.96, when we round up, would become 0.10 in one single digit. So we end up rounding to the nearest whole anyway, so it's 73 degrees. There's our angle A. That is the largest angle, which for this particular problem, what that means is we couldn't have screwed anything up. We could have done them in any order. But again, we don't know that to begin the problem. No one does. You might do 1,000 of these and have an inclination. But even after that many, you're not going to know. I will be 100% honest with you. I don't know when I start these problems unless I already have done them, whether it would be a problem or not. I have a way of creating them to make sure one of them is bigger than 90. I can do these problems backwards and reverse engineer them is the way I do it. But I can't just make up numbers on the fly and guarantee it's going to work unless I make two of the three just absolutely ridiculous. All right, so now we have angle A. There's two angles left. The next step is always law of sines to make it easy. Yes, we can certainly do law of cosines to find all three of these. And if you did that, you would guarantee that you never have to worry about any of those angles being incorrect because you're never doing an inverse sine. But you saw how much math we just did to get that angle. Do you want to do that 2 more times, or would you rather do law of sines and then 180 minus? Yeah, I'm going to do that. So the second step, we put down here, that's the law of sines. And it doesn't matter which one we pick. So the completed one is the A's, so we got 12 over the sine of 73 degrees. And let's go after the B's. I'll go after the smallest one because, like I said, it doesn't even matter. 9 over sine of B. You're going to cross multiply, and you'll get 12 sine of B equals 9 sine of 73 degrees. You're going to divide by the 12. I'm going to stop writing all the little details because this is the 50th time we've done it now. So we get that the sine of angle B is 9 sine of 73 degrees over 12. Yes, you can reduce the 9 and 12, but nobody cares. Take the inverse sine of both sides, and you'll get B equals inverse sine of 9 times the sine of 73 degrees over 12. Rounding to the nearest tenth. Second, sine. 9 sine 73, close it, divided by 12, close it. And we get 45.8 blah, 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 rounding to the nearest tenth, so just 45.8. That's an angle, so degrees. You could use law of sines to find the third one. You could use law of cosines to find the third one. Both of those are going to be way longer than just doing angle C is 180 minus the others. That's that 107, 67, 62, 61.2. Yes, I do my subtraction from left to right. I'm a freak. Don't be mad about it. I don't know what it is, but it's easier for me to subtract in my head from left to right than right to left. You don't have you just have to kind of predict the borrowing. And it might sound weird, but if you do it a million times, it's easy. So that's our angle C. And there we go. We were given 3 sides. We found 3 angles, and they're going to be pretty accurate. So this is the first problem I've given you so far that you couldn't have screwed up by not attacking the largest angle first. But again, we didn't know that to begin with. We had no way of knowing that to begin with. All right, with our last 15 minutes, let's rock this last one. I thought we'd get to finish early, but yeah, not so much. That's okay. We got class time, we're going to use it. Give you another image. Let's go 10, 15, 18. And by my choice, I'm going to call angle A the 18. If you're given the choice, maybe you just always make A the largest one, and that would be a helpful reminder to just always attack the A's. I'm going to call B this one and C this one, or maybe you just always go A, B, C in that order. I don't know, I don't care. If you're not told what letters they are, make your choice, make it good. So we must attack angle A first because that's opposite the largest side. We have no other choice because things could go wrong otherwise by the end. This angle will be right, but others might be wrong. All right, so going after angle A, that means I need the one that says A squared equals blah, blah, blah. So that'll be 18 squared equals 10 squared plus 15 squared minus 2 times 10 times 15 times the cosine of angle A. What's 18 squared? I don't feel like doing that in my head. That's 324. 10 squared is 100. And then 15 squared, that's 225, right? Yeah, 225 plus 225. Then minus, that's 20. 20 times 15 is going to be 300. Cosine of angle A. The 100 and the 225 are going to make 325. Subtract 325 on both sides. Remember, you can't subtract the 300 because it's got the cosine term. So we get -1 equals -300 cosine of angle A. Divide both sides by -300. Up here, so that gives us 1/300 is equal to the cosine of angle A. Take your inverse cosine of both sides. So the inverse cosine of 1/300 would be your angle A. Now that's 100% accurate, but you know that we want to approximate that to the nearest tenth. So second cosine, 1 divided by 300. Close it, drum roll. We get something really, really, really close to would have caused a problem later. But that largest angle is 89.8. So again, for this one, we would have been lucky, and any order we did, it wouldn't matter, but we didn't know that to begin with, so trust me, do this one first. So that says 89.8 degrees is about angle A. We got our first one. So that was our law of cosines. Now we go to law of sines. Let me just put that on the next page. Law of sines, doesn't matter which one we grab since we already have the biggest angle. We know the others have to be less than 90 degrees for very obvious reasons. So what do we have completed? We have the A's completed, which is 18 over the sine of our 89.8 degrees. And then we can go after the B's or the C's. It doesn't matter, I'm gonna go after B's because alphabetical order. So 10 over the sine of B. You're gonna cross multiply and you'll get 18 sine of B equals 10 times the sine of 89.8 degrees. You're gonna divide by the 18. So we get sine of B equals 10 sine of 89.8 degrees divided by the 18. Then you take your inverse sine and you get angle B equals inverse sine of 10 times the sine of your 89.8 degrees. We're almost there, all over your 18. That's an ugly 8. Let's try that one more time. There we go. Nobody said my handwriting was pretty. So inverse sine times the 10 times the regular sine of 89.8. Just imagine if you get one of those sines or inverse sines backwards. Everything's wrong. Divided by the 18. And we get 33.7 when we're round to the nearest tenth degrees. So that's our angle B, which means our third angle, which we called C, is 180 minus the others. What's that gonna be? 90.2, 60, 56.3. No, 56.5. 0.2 minus 0.7, 56.5 degrees. I don't know why I said that first one. So that would be our C rounded to the nearest tenth. A, B, C, and we got them. We're good. Oh, we did finish a little early. Sweet. We got a little more efficient at it. At least I hope we did, because no one said anything. So that is 8.2. We managed to finish that section in a day. That's really tough in a trig class to actually finish any section in one day. So, and I think I just said 8, and I was about to write it as well. It's 7. It used to be chapter 8. So 7.2 will be due. Today's the 11th, so the 18th. So I will make sure that due date is set up in my math lab later today. Not that it matters. You can always work on it even if I set up the due date later. All right. So I don't want to take the last 5, 6, 7 minutes we have left to start vectors, but just note that starting in next class, we're going to start plotting a lot of things that look like this. We'll have these little dots and arrows, and these are known as vectors. And no, we're not talking about the same thing from Donnie Darko. I know everyone likes to use that as a reference. If you remember that movie, if you're too young for the movie, then if you want to go see a weird movie, go watch Donnie Darko. It has nothing to do with math, but they use the term vector. And it's kind of an arrow, but it looks really weird because 1990s CGI. 90s, not 90. All right. So we'll call it a day there. We'll pick up with the vector stuff next class. I might even have a test date for you coming up because just like test 2, there aren't a lot of sections that we'll have in test 3. But besides that, email me with any questions. I'll get the homework set up. This video will be posted on YouTube later. Have a good day.